Hi friends, in this video we find the method to evaluate residues. So we are having three different cases to evaluate the residues, right? So let us see that. I apply the formula only, concepts and all I won't explain, right? But I will explain how to solve the problem in the simplest manner. Let us see, right? So residue at a pole A, residue at a simple pole. Let us assume we have a pole. I will tell you how to find the pole. Residue at a simple pole A, pole of order 1 is given by residue f of z. Z is equal to A. Let z tends to A. So limit z tends to A. Z minus A into f of z. This is a residue at a simple pole. Let us assume this case 1. That is pole of order 1. That is given by limit z tends to A. Z minus A f of z. Right. Second one, if f of z is function of z in numerator and function of z in denominator, where denominator has a value of 0 when you substitute pole, but the numerator is not 0, that means psi of a, psi of z, z is equal to a, we substitute. That is denominator 0 and numerator is not equal to 0 at z is equal to a, then residue is given by limit z tends to a, z minus a, f of z. This one is equal to phi of a and psi dash of a. Psi dash of a is nothing but differentiation of psi of a, right? So we have to keep the numerator as it is, but we have to differentiate the denominator. I will give the example, right? Then you will understand. Then third one, residue at a pole of order m, right? In first case, this is a case 3. In first case, we found simple pole order 1. Here residue at a pole of order m is given by z is equal to a is a pole, right? A is a pole. So residue at pole of order m is limit z tends to a 1 by m minus 1 factorial d power m minus 1 divided by dz m minus 1 z minus am f of z, right? So these are all the three cases. So simple pole, when numerator and denominator are there, numerator is not a function 0 and denominator is 0. This is a case 2. Case 3 is pole of order 3. And one more thing we have to remember about residue case is this is another important definition. This definition is helping you to solve the problem. The residues are the coefficient of 1 by z in the Lorentz expansion of f of z. So if you are able to expand f of z in terms of Lorentz series, and the coefficient of 1 by z is given by residues, right? This also we will use to solve the problem, right? Okay, so 4 points we have to remember. By using this 4 points, we can solve any problems, right? Okay, let us see. The first question is find the residue of f of z 1 by z square plus 1 whole square about z is equal to I. Yes, this is the question. So f of z is equal to 1 by z square plus 1 whole square. This is the question. For that, I have to find the residue at z is equal to I. Okay. So first we have to find whether it is a this function as simple pole or pole of order 2 or 3 or 4, right? So let us assume f of z is equal to 1 by z minus 2. Pole is a value of z which makes your function infinity. So when you substitute z is equal to 2, it will become infinity. So z is equal to 2 is a pole, right? It is a simple pole, right? Pole of order 1 because it is power 1. Suppose f of z is equal to 1 by z minus 2 whole square means here also pole is 2, z is equal to 2 is a pole. This is pole of order 1, other name is simple pole. It is pole of order 2 because we have two poles, that is equal to 1 by z minus 2 into z minus 2. So that's what it is, pole of order 2. So we have z1 is equal to 2, another pole is z2 is equal to 2. So here you see what value of z makes f of z infinity, z is equal to plus or minus I, which makes z is equal to f of z infinity. So it is a pole of, here you see order is 2. So it has poles at plus or minus I and a pole of order 2. F of z as pole of order 2, right? We know that for pole of order m. What is residue of f of z? Residue f of z, z is equal to a is limit z tends to a, right? 1 by m minus 1 factorial d by dz z minus a whole power m into the f of z, right? So this is what the general formula, pole of order m, right? So you see what is the formula? Pole of order m is z tends to a 1 by m minus 1 factorial. Sorry, it is d power m minus 1 by dz by minus 1, right? So differentiation, I forgot to write. So I write it d power m minus 1 dz m minus 1. Right, here m is equal to 2 because pole of order 2. M is a order of the pole. Fine. So now we substitute. A is pole. What is the pole? I, right? So let us substitute z is equal to I because we are going to evaluate at z is equal to I only. No need to take care of minus I. So z is equal to a. So a is I. Limit z is equal to I 1 by 2 minus m is equal to 2 factorial d power 2 minus 1 d power d is 2 minus 1 d. So z minus a is I 2, m is equal to 2, f of z is 1 by z square plus 1 whole square. Alright, so if you simplify, what we get is limit z tends to I, right? It is 1 by 1 factorial is 1 d by dz. This is z minus I whole square into z square plus 1 I can write as z plus I into z minus I. This is z square plus 1. It is z square plus 1 whole square. So I again write it as z plus I into z minus I. So z minus I whole square cancel. Fine. So what we get is, so this is equal to limit z tends to I d by dz 1 by z plus I whole square, right? So what I do is I simplify. So limit z tends to I d by dz z plus I whole power minus 2. If I simplify, what I get is limit z tends to I minus 2 z plus I minus 3, right? I differentiated. So what we get is, if you simplify, limit z tends to I minus 2 divided by z plus I whole cube. You substitute I value, z is equal to I, so it will give minus 2 by 2I whole minus 2 by 2I whole cube. That will give minus I by 4. So the answer is minus I by 4. So option D is a correct answer, right? So tedious problem, but easily we can solve, right? Okay. Next question. Find the residue of f of z, which is equal to z into e power minus 1 by z square at z is equal to 0. Here you see, first we have to check whether it is, we can find pole. No, pole means we should have denominator. So we denominator as a function of z. So here we cannot have a pole. So we have to go for other method of evaluating the pole. What is that? Let us see. We have studied one more thing. What is that is, you see, residues are the coefficient of 1 by z if you expand the given function by Lorentz expansion. So I try to expand this equation by Lorentz series, right? So it is very easy to expand Lorentz series. How can we expand? We know how to expand Lorentz series. Z into e power minus 1 by z square. This we can expand as, first we expand in the binomial format. So you can expand by binomial format, right? Z into, it is e power x format, e power minus x. So 1, right? So I consider minus 1 by z squared as x, right? So what is the formula expansion for e power x? 1 plus x by 1 factorial plus x squared by 2 factorial, like that it will go. So z I keep it outside. E power minus 1 by z square, right? I write as 1 plus minus 1 by z square divided by 1 factorial. Instead of x, I take minus 1 by z square plus minus 1 by z square whole squared by 2 factorial, like that it will go. But what I need is coefficient of 1 by z only, right? So what is the coefficient of 1 by z? If you bring a z inside, it is z plus minus 1 by z. 1 by 1 factor is 1, right? Like that I want only the coefficient of 1 by z. What is the coefficient of 1 by z? Minus 1. So that is a residue. So coefficient of 1 by z is minus 1. So the answer is minus 1, right? So option A is the right answer. And the next question is find the residue of z into cos z, cos 1 by z, right? So here also you see cos 1 by z I can expand by using Lorentz expansion. So here we don't need to go for poles, right? It is very difficult to find the poles because it is not a function of 1 by denominator of z, right? So what I do is z into cos 1 by z I expand as, we know cos x can be expanded as what do you call, 1 minus x squared by 2 plus 2 factorial plus x power 4 by 4 factorial minus x power 6 by 6 factorial, like that it will go. So here I consider 1 by z as x. So z into cos I expand as z into 1 minus 1 by z whole squared by 2 factorial. I need coefficient of 1 by z only, right? Because whenever you use Taylor series, Lorentz series, coefficient of 1 by z will give residue. So I don't need to expand beyond that. So I stop here itself. Z into z I bring inside. This is 1 by z squared. So z by 1 by z. So 1 by z into 2, right? So this implies what is the, this is z minus 1 by 2 z. What is the coefficient of 1 by z? Here the coefficient of 1 by z is minus 1 by 2. This is the coefficient of 1 by z. Therefore, residue is minus 1 by 2. Simple problem. Right? So, next one, here you see, find the residue of z plus 2 divided by z minus 2 into z plus 1 whole square. So, it is a numerator is a function of z, denominator is a function of z. So, we can find pole. So, what are the pole? Right? Pole is a function which makes the total function, pole is a value of z which makes total function infinity. So, let us assume f of z is equal to z plus 2 divided by z minus 2 into z plus 1 whole square. So for what value of denominator z, the function becomes infinity? Z is equal to 2. If you substitute z is equal to 2, the function becomes infinity because 1 by 0. So z is equal to 0 is a pole of order 1 or simple pole. Then what is the other pole? Z is equal to minus 1. When you substitute z is equal to minus 1, it will become 0. So the function becomes infinity. So z minus 1 is a pole of order 2. That means we have two poles at z is equal to minus 1. Right? So we know how to find the residue for pole of order 1, simple pole. So residue at z is equal to 2 is given by, simple pole means limit z tends to 2, z minus 2, f of z. F of z is z plus 2 divided by z minus 2 into z plus 1 whole square. Why? For a simple pole, what is the formula to find the residue? Z tends to A is a pole, z minus A into f of z, right? So here A is 2, A is a pole. So this 2 will be cancelled. 2 substitute Z is equal to 2, 4 by 3 square 9. So one residue is 4 by 9. We have a residue of 4 by 9 at Z is equal to 2. But Z is equal to 1, minus 1 is a pole of order 2. For pole of order M, what is residue? That is given by limit Z tends to minus 1. 1 by M minus 1. M is pole of order 2. So M is equal to 2. 1 by M minus 1. So 2 minus 1 factorial d power M minus 1, that is d power 2 minus 1 d is Z power 2 minus 1, right? Z minus A, Z minus of minus 1, so Z is Z plus 1 M. M is nothing but 2 f of Z. F of Z is Z plus 2 divided by Z minus 2 into Z plus 1 whole square. What is the formula? Formula to find the pole of order M, residue at pole of order M is Z tends to A. A is minus 1. 1 by M minus 1 factorial. M is 2. D power M minus 1. D Z power M minus 1. Z minus A whole power M into F of Z. That's what I have done, right? So these two fellows will be cancelling, right? So what you get is limit Z tends to minus I d by dz into Z plus 2 divided by Z minus 2. Differentiate and substitute the value of minus 1. Minus I, what you get is minus 4 by 9. Right? Differentiate this, substitute Z is equal to minus I. We get residue of minus 4 by 9. Right? Simple problem, but tedious. Okay, next problem is find the residue of cot Z. So first thing is I don't have numerator. This f of Z is not a function of numerator of Z, denominator of Z. So poles we cannot find. And I don't know how to expand cot Z in Laurent series. So what I do is I go for third method. F of Z is phi of Z divided by psi of Z. Right? In that way we will find. So I expand in terms of numerator of Z. So cot Z is cos Z divided cos Z by divided by sin Z. What is the pole here? Here pole is what is the value of Z that makes function infinity. So when Z is equal to n pi, the function becomes infinity because sin n pi is 0. So 1 by 0 infinity. So Z is equal to n pi is a pole. N is equal to 1 sin pi, n is equal to 2 sin 2 pi, whatever be sin pi, 2 pi, 3 pi, everything is 0. So it is a pole, simple pole, right? But you see when you substitute Z is equal to n pi, sin n pi is 0, cos n pi is 1. So here, right, numerator does not equal to 0, denominator is equal to 0 at n is n pi. You remember one case, I have given one case, let us go there and see. Right, so I told one thing, right? Case 2, when numerator is 0, sorry, numerator non-zero, pi of Z, and denominator is 0, what we have to do? We know Z is equal to n pi there in our problem. Pole, A is a pole, so we have n pi as a pole. What we have to do? Keep numerator as it is and substitute n pi value, but differentiate denominator and substitute pole value, that is n pi. So what we are going to do is I am going to keep numerator as it is and differentiate the denominator as per the case 2 because numerator is non-zero, denominator is 0. So residue at residue of f of Z at Z is equal to n pi is given by keep numerator as it is, differentiate denominator with respect to Z, so it is cos Z. Now you substitute Z is equal to n pi, it will become 1. So the residue of cot Z is 1, right? It's a way to solve. So I hope understand how to find a residue. All the different methods I have shown, you can clear any questions from this area if you watch this video. I hope you understand. Thank you.